Hello, everybody. Welcome to the Georgia Tech Graph Theory Seminar, the first seminar of the spring 2021 semester. And our speaker today is Guo from Georgia Tech, who is going to talk about Prague dimension of random graphs.
Okay, so thanks for the invitation and thanks for the introduction. Today I will talk something that is based on joint work with Kalen Patton, with an undergraduate student at Georgia Tech, and my advisor, Lutz Warnke. So before I move on to give the formal definition of what is Prague dimension, let me give you some high-level idea about the parameter Prague dimension we will talk about. So actually this parameter is related to the following complexity concepts. There are three kinds of these concepts, which is about representation, which is about you are trying to efficient encode some objects. And it's also related to decomposition, which you divide an object into few-based simpler objects. And Prague dimension also related to some dimension, which is about embedding an object into the minimum number of one-dimensional objects. So I hope I gave you some taste about this parameter. And actually this parameter was introduced by Nešetřil, Pultr and Rödl in the late 1970s. And there are many equivalent definitions of this Prague dimension. Therefore, this is a natural notation. And we will introduce the definition in next slide. And to study this parameter, the Prague dimension, previously many approaches have been applied. For example, the algebraic and combinatorial and some information theoretical ones. And typically to determine the Prague dimension of some general graph, it is an NP-hard problem. Therefore, as you can see, the determining the Prague dimension is an interesting but hard problem. So in this talk, I will introduce a recent result that determines the order of Prague dimension of random graphs, and it resolves Prague dimension conjecture of Füredi and Kantor. Oh, let me mention that in this talk, feel free to interrupt me if you have any questions, so you can unmute yourself or you can type in the chat. Okay, so that's the background. And then we can move on to define the Prague dimension. So here is the definition of Prague dimension of our graph G. So Prague dimension of our graph G is a minimum K such that there exists a K-calibrable K covering of the complement of the graph G. So let me explain the terms over here. So what is the click covering? So click covering of a graph is a collection of clicks in a graph that covers all the edges of the graph. For example, if you have the graph over here, they make a click covering because each edge is covered by one of the clicks. So they form a click covering. And we see a click covering is K-colorable if we can assign different colors to the clicks so that the clicks in the same color class receive different colors. Oh, sorry. The clicks in the same color class are vertex disjoint. So for example, here if we have this click covering, and you can figure out that the chromatic number of this click covering is 3, because these 3 clicks share this vertex. Therefore, they must receive different colors. Therefore, you can figure out the click chromatic number of this click covering is 3. Therefore, the Prague dimension is the minimum K, minimum chromatic number over all click covering of the complement graph of G. So this parameter was introduced by Nešetřil, Pultr and Rödl in the late 1970s. There are many equivalent definitions. So I gave this click-based one over here because it's easier for our analysis later. And for brevity, here we just define the click chromat number of G to be the minimum chromat number over all click covering of G itself. Therefore, it is a complement of, that is Prague dimension of the complement graph of G. Okay, so is there any question about the definition? I hope everyone can understand this definition because later on we will focus on the click chromat number over here. So that is the minimum chromat number over all click covering of G. So is there any question at this point? Okay, so let's move on. So here we give the definition. And what's the problem? The problem is that we try to work on the conjecture by Füredi and Kantor. So they conjecture that the Prague dimension of the binomial random graph GNP is with high probability has the order of magnitude n over log n for all constant p. So here the binomial random graph GNP is the n vertex graph that each of the n choose two pairs is included in GNP independently with probability p. So let me give you some motivation of such problem, why it's interesting. Because when p is equal to 1/2, the binomial random graph Gn 1/2 is just take each of the n vertex graph uniformly at random. Therefore, this conjecture says that almost all the n vertex graph has Prague dimension roughly n over log n. And actually, for some graph G, the Prague dimension can be as large as n-1. So this conjecture says that this case is an extraordinary case, so they are rare. Therefore, the Prague dimension of graph, which is much larger than or much smaller than n over log n, is the rare case. And to prove this conjecture, it's actually enough to show that the click chromat number of GNP has the order of magnitude n over log n. So that is because by definition, we know that the Prague dimension of GNP is just the click chromat number of the complement graph of GNP. And the complement graph of GNP just has the same distribution as the binomial random graph Gn 1 minus p. And because p is a constant, so it's enough for us to show that for all constant p, with high probability, the click chromat number of GNP has order of magnitude n over log n. Actually, to prove this bound, the lower bound part is simple. That is because to prove a lower bound of click chromat number of GNP, we consider our vertex with maximum degree. And because we need to cover all the edges incident to this vertex by some clicks, therefore we need at least the maximum degree of GNP over the size of maximum click in GNP minus 1. So we need at least so many clicks to cover the edges incident to this vertex. And another observation is that for all the clicks that contain this vertex, we need to give them different colors so that the clicks in the same color class are vertex disjoint. Therefore, for those clicks containing this vertex, we need to give them different colors. Therefore, we need at least so many colors. Therefore, the click chromat number of GNP is at least this number. And we know that with high probability, the maximum degree of GNP is roughly n times p, and the maximum clicks of GNP has size roughly 2 times log n, where the base is 1 over p. Therefore, as you can see, the lower bound part is simple, and therefore, actually, we need to prove the upper bound. So that is the difficult part. And also this bound suggests that we need to deal with clicks of size roughly log n. So that will be the difficult part. And we will put more focus on the upper bound. So is there any question about this problem?
Is there a conjecture for actually what the constant should be as well in front of n over log n?
No, so actually their conjecture does not depend on p because p is a constant. So actually you can conjecture the bound look like n times p over log n where the base is 1 over p, but actually because p is a constant, that doesn't matter.
Right, I was just curious if, yeah, so we expect that really this lower bound is correct, even with the constant.
Yeah. So actually at the end of the talk, I will see that actually this lower bound is not correct. If you consider about the asymptotics, not just the order of magnitude. We will discuss later.
Okay.
So is there any other question? Okay, so let's continue. So that is the main problem. We try to figure out the order of magnitude of the click chromat number of GNP. And our main theorem states that we know that with high probability, the click chromat number of GNP has the order of magnitude n over log n for all constant p. So because the relation between Prague dimension and the click chromat number, we verify the Prague dimension conjecture of Füredi and Kantor. And also for this result, we can extend to the case that the probability p can be a function depending on n and tending to 0 as n tends to infinity. So we also determine the asymptotics in this case. And our result can also extend to the edge partition case. So what is the edge partition case? So here the click chromat number is the minimum chromat number over all click covering of GNP. So for the click covering, we only require that the clicks cover all the edges of GNP. So we can further require that we need to take click covering, that the clicks in the collection are edge disjoint. So if we define some parameter so that the minimum chromat number over all the click covering where the clicks are edge disjoint, we can also determine the order of magnitude of that parameter. So actually that parameter also has order of magnitude n over log n. So actually the edge partition case is even stronger than this result. Well, today I only focus on this result itself. And so what is the motivation for us to study this problem? One reason is that, as I mentioned, when p is equal to 1/2, the binomial random graph Gn 1/2 is just to take all the n vertex graph uniformly at random. Therefore, our result states that almost all the n vertex graph has click chromat number and Prague dimension roughly n over log n. And the second reason is that to prove this kind of result, it is about covering and decomposition problems, which was also studied previously. So for example, if we take the minimum over size of the click covering of GNP, so Füredi and Rödl shows that the minimum size has order roughly n square over log n square. And if one takes the minimum over maximum clicks, maximum degree of the click covering of GNP, so that has order of magnitude roughly n over log n. So here the maximum degree is that you can view the click covering as a hypergraph where the vertices are 1 to n and the hyper edges are just the vertex size of the clicks in the click covering. Therefore, the maximum degree of the click covering is just the maximum number of clicks containing a fixed vertex. So it says that this parameter has order of magnitude roughly this one. So actually, you can show that the click chromatic number is at least this maximum degree, because for all the clicks in the click covering containing a fixed object, a fixed vertex, they need to receive different colors. Therefore, this is a lower bound, but as we discovered, we need an upper bound. So actually, our result is stronger than this result. And our result also implies these two results. So to prove our result, we combine some random greedy paradigms, which I will introduce in the next slides. Okay, then I will go to talk about the proof strategy of our result. So is there any question about our main theorem? Okay, so I hope everyone feel happy at this moment. Okay, so then let's move on. So we are going to prove actually the upper bound part. So to prove one upper bound of the click chromatic number, what we need to do is we need to find, with high probability, we can find a click covering that is click chromatic index is at most roughly n over log n. And here is our proof strategy. First, we try to find the click covering. We find a click covering, and we actually find the click covering via some semi-random algorithm, which is also called Rodoniibo Method. So to find the click covering, at each step, we find the subcollection of clicks step by step. So there's C0 to C capital I, and then we take union of them to be our click covering. Then we get our click covering. Next, we need to show that the chromatic index of this click covering is at most roughly n over log n. And the idea is that because this click covering is just a union of the subcollections, therefore the chromatic index is at most the sum of the chromatic indexes of the subcollections. And we only need to bound the chromatic index of each subcollection. And we will use some chromatic index result for hypergraph. And to prove that the result, we need to apply some random greedy algorithm. So that is just a high-level idea of the proof strategy. And then I will talk a little bit about the two parts of the proof. So for the first part, we try to find the click covering. So how do we find the click covering? As discussed, we will use some semi-random algorithm. So the idea of the algorithm is that we start with G0 equal to the binomial random graph GNP. And from each GI, we random select some large clicks. So in each GI, we random select some large clicks, and we form, we let them to be the collection of clicks CI. And then we remove these large clicks from GI to get the graph GI plus 1. And we do it iteratively. And after capital I step, here we get the remaining graph GI. And we take all the remaining edges to be clicks of size 2. And we form them into CI. Therefore, we find all the subcollections of clicks C0 to CI, and then we take union of them to be the click covering we are looking for. So as you can see, this collection of clicks C is really a click covering because all the edges of the original graph G0 is covered by one of the clicks in this collection by our algorithm. And therefore, we get our collection of clicks. Also, that is the click covering. And the key property here is that at each step, the remaining graph GI behaves like a binomial random graph Gn pi for some exponentially decreased pi. Actually, to get this key property, we need some actual technical twist, but I do not want to mention it here. One thing I like to mention is that the clicks we included into each subcollection, into each collection CI has size roughly some small constant a times log n, where the base is 1 over pi. So as I mentioned, for the largest clicks in the binomial random graph GNPI, the maximum click has size roughly 2 times this log parameter. And as you can see, actually, indeed, we remove some large click at each step. And they can be as large as some log n. Okay, so that is the first part of our proof. So about how to find the click covering C. So is there any question about this part? Okay. If not, let's move on to the second part. So at this part, we already found the click covering of GNP. And the next part is that we need to bound the chromatic index of this click covering. So that is second part. Because the click covering is just a union of those collections, therefore the chromatic index of the click covering is just as most the sum of the chromatic indices. We claim is that if we can show that for each subcollection, the click chromatic number is at most some universal constant times the maximum degree of this collection of clicks, then we will complete our proof. So recall that the maximum degree of the collection of clicks is that we will the collection of clicks as a hypergraph, where the vertices are 1 to n, and the hyper edges are just a vertex side of the clicks in the click collection, CI. So that is the max number of clicks in CI that contain a fixed vertex. So we claim that if we can show this kind of bound, then we will complete our proof. So that is because if we consider the maximum degree of the collection of clicks CI, so that is roughly at most the maximum degree of GI, which is roughly n times pi over the clicks in the click collection CI, because we need to cover all the edges in sentinel vertices. So, and here we use the clicks of size roughly this one. And another actual property is that actually the clicks in the CI are almost edge disjoint. Therefore, we need at most the maximum degree of GI over the clicks of this size. And because the graph GI behaves just like the binomial random graph GNPI, therefore the maximum degree of GI is roughly n times pi. And if you do some mathematical computation, you will figure out that this sum is at most what we are looking for. Therefore, if we can show that the click chromatic number of the click CI is at most some constant C times the maximum degree of the CI, then we will finish our proof. So, and actually for the last step, when I equal to capital I, because we take all the edges of the remaining graph GI to be the final collection of clicks, So that is just a graph. Therefore, by Weyer's theorem, we know that the click index of that graph is at most 2 times the maximum degree of that graph. Therefore, this one we get it for free by Weyer's theorems. And when I is at more, when in the previous step, to get this kind of bound, because the collection of clicks CI contains clicks of size greater than 2. Therefore, we really need to deal with some hypergraph case. That is a place where we need some Pippenger and Spencer-like result for hypergraph. So what is a Pippenger and Spencer-like result? Let me give it over here. So that is a famous theorem by Pippenger and Spencer back to 1989. So that is a result about chromatic index for hypergraph. So their theorem states that if you have some constant k, some small epsilon, so if you have a k uniform n-vertex hypergraph H, then the hypergraph H, we require the hypergraph H to be nearly regular, which means for almost all the vertices of H, they are in the roughly same number of hyperedges of H. And the hypergraph H also has small code degree, which means for any 2 vertices of H, they are in a small number of hypergraph. So if you hypergraph H satisfies this requirement, that is nearly regular and has small code degree, then the chromatic index of the hypergraph H is at most 1 plus epsilon times the maximum degree of H. So here the chromatic index of H is just the minimum number, so that you can color all the edges of H, so that edges of H in the same color class are vertex disjoint. So they claim that if you hypergraph H satisfy this requirement, then the chromatic index of H is at most 1 plus some epsilon has a maximum degree of H. And actually, you have that the chromatic index of H is at least the maximum degree of H, because for all the edges containing a fixed vertex, they need to receive different colors. Therefore, they claim that the chromatic index of H is roughly the maximum degree of H when your H is nearly regular and has small code degree. And we like this kind of result because here you have the universal constant, roughly 1 plus epsilon. We want this kind of result. But unfortunately, we cannot use the Pippenger and Spencer result directly. So that is because in the Pippenger and Spencer result, the uniformity of the hypergraph H need to be a constant K. But recall that, as I mentioned, for the clicks in the collection CI, they can have size as large as log n, which is not a constant. So we cannot apply Pippenger and Spencer result. But because the collection of clicks CI is some random random set, then we can actually extend the Pippenger and Spencer-like result to the uniformity case, roughly log n. So I will introduce the result.
Just as a comment, so this is like a major technical problem here. This is not just something that came up and needs to be overcome. Like the fact that this Pippenger Spencers for constant k, like maybe if you work hard, you can let k grow a little bit, but to do it all the way up to log n is like not at all clear how to do it in general. Like this is I think that was the reason why this problem beforehand was not solved.
Yeah. Yeah, so actually our result is not just extending the Pippenger and Spencer result directly. We use some different method. Okay, so here is our chromatic index result for random hypergraph. So this result states that if your host graph H is a K uniform, an n-vertex hypergraph, And it satisfies the following properties. So first, the uniformity is at most some constant b times log n. So the uniformity can be as large as some log n term. Secondly, if your host graph H is nearly regular, which means for all the vertices of H, they are in roughly so many number of edges of H. And the third one is that if your hypergraph H has small codegree, which means for any two vertices of H, they are in at most so many number of hyper edges. Then our results decide for the random hypergraph HM, where the edges of HM are just E1 to EM, and each EI is chosen from H uniformly at random. So if this is your random subhypergraph HM, where you M need to satisfy that M is not too small, and M is much smaller than the number of edges of the host graph H, then we claim that with high probability, the chromatic index of HI is at most 1 plus some constant delta times the maximum degree of the random hypergraph HI. Here, the constant delta satisfies this relation. And the key point for our chromatic index result for hypergraph is that it allows edges to have uniformity log n. And as a corollary, if your host graph H has a uniformity, some little o log n term, then here you can choose B to be some little 1 term. And by this relation, you can figure out that your delta over here can be some little 1 term. Therefore, you get the Pippenger and Spencer-like result, 1 plus little 1 term times the maximum degree. And if you uniformity of your hypergraph H, it really has uniformity roughly B times log n, then you need to choose B a little bit larger. Therefore, your constant delta is no longer a little 1 term, but some constant term. And therefore, the chromatic index of HM is at most some constant times the maximum degree of the random hypergraph HM. And actually, this is a case that we apply to our proof of the clear chromatic number, because as a hypergraph, CI is just the hypergraph, where the vertex side is 1 to n, and the hyper edges are the vertex set of cliques in the clique collection, CI, and we need this kind of result. So actually by our chromatic index result for random hypergraph, because our CI is also chosen randomly, it gets this kind of bound, and we will complete the proof of our clique chromatic result. Okay, so at this point, we have finished the proof of our clique chromatic number result. Is there any question about this clique index result for random hypergraph? Because later on, we will mainly focus on discussing this result. So is there any question about the statement of this result?
So if you let k be even bigger than log n, let's say, then can you get some weaker bound where you replace a constant by some other function?
Yeah, I think in that case, our proof may have some problem. So that is not very easy if you replace B by some something 10 to infinity. Yeah, that is some restriction in our proof.
I'm willing to say maybe the proof gives something, but we have not thought at all about what the proof gives. It certainly starts degrading at log n. I'm not sure if the following is some evidence that also something else happens there, but I know that if you want to prove a deterministic Pippenger-Spencer result, that Pippenger-Spencer cannot be true if k is much bigger than log n. So you can construct examples where this epsilon has to blow up if you go beyond log n. So there is some kind of phase transition happening at log n, even for the general deterministic case. What exactly would happen in the random case, we have not explored that.
Sorry, is it important that this hypergraph is a uniform hypergraph, or can it be generalized to non-uniform hypergraph, but the uniformity is within a certain bound?
Yeah. Let me think a little bit about. I think our proof technique does not apply to that case, but typically when we deal with that situation, we try to decompose the hypergraph into some uniform hypergraph, and then you sum up the chromatic index, if that will be helpful. But I think our technique does not apply to that case if the uniformity is not same.
Thank you.
Okay, then we will go into
just one question to us: does anybody know if there's the Pippenger-Spencer type result in the deterministic case where you allow for different sizes? Does this ring a bell to someone? Or an application where this would be useful? Maybe I tend to, in this context, like to ask what is the application, because you can prove all kinds of technical statements in the end. Be nice to have. Do you have anything in mind?
It's just like, so here it seems like the application here is that all the clicks are picked out are the same size, right? But then if we allow the click size to be within a certain asymptotic size, and then I'm not sure whether, but it's even with a constant size it will work in this setting. But
I was asking, like, if you have any application or problem in mind where or any setup where this would arise. That's what I was.
Not off the top of my head, but I'm thinking if there's like a click decomposition, then does it have to be like when we do the analysis, does it have to be the same click size, or can it be the same group of click sizes?
Mm-hmm.
But I don't have.
I think we would have to look into this. I think the difficulty is if you have these of different sizes, then the rate at which certain edges get killed off are closely related to the sizes somehow. And one needs to look into it. I have not thought about it. Okay.
Okay, then we will move on to discuss a little bit about the proof idea of this chromatic index result for random hypergraph. So how do we prove this kind of result? So actually we have some natural random gradient algorithm so that we can color the edges of the random subhypergraph HI using just so many colors. And using so many colors is enough if we can show that this number is roughly the maximum degree of the random hypergraph HI. So that is true because we have the random hypergraph HI. Then the maximum degree is just because we choose the random hypergraph HM uniform and random, therefore the maximum degree is just the maximum degree, roughly the maximum degree over the fraction of the number of HM, which is M, over the total number of edges of the host graph H. And because your host graph H is a nearly regular hypergraph, therefore the maximum degree is roughly D. And because it's nearly regular, so the total number of H is just N times D over K. And actually this number is equal to this one. Therefore, if you can prove that you can color the edges of HM using so many colors, that will be enough. And actually we read some natural random greedy algorithm to achieve this goal. And our analysis is based on the differential equation method, which I will introduce in next slide. So first, what is the random greedy algorithm to color the edges of HM? So that is very simple. So we let the set Q from 1 to Q to be the set of all the possible colors. And the algorithm runs as the following. So for each step, we sample one of the edges of the host graph H uniform and random. And then we color the edge by an available color, uniform and random. So we say a color is available if that color is not used in any previous edge that intersect with edge E. So here is an example about how the algorithm runs. So here is your hypergraph, where each black dot is vertex, and the line crossing the vertices hyper edge. So this is a 3 uniform hypergraph. And we may assume we have 4 possible colors, red, blue, green, and yellow. And then we try to run the algorithm. So as the first step, we sample one edge uniform at random. For example, this edge. So at this moment, all the 4 colors are available to this edge. And we select one of them uniform at random. For example, we select red, and then we color this edge by red. And then we move on to next step. So in the next step, we sample another edge uniform at random. For example, this edge. And at this moment, all the 4 colors are still available. And we choose one of them uniform at random. So for example, green. And then we move on to next step. So for example, at this step, we sample this edge. But at this moment, you can see that you only have 2 available colors because this edge is incident to a red edge and incident to a green edge. So red and green is no longer available. So you only have 2 available colors, blue and yellow. And then we choose one of them, uniform at random, for example, blue, and then we color this edge by blue. And then we continue to next step. For example, we sample this edge. And as you can see, the red and blue and green are no longer available for this edge. Therefore, you only have 1 available color, and we color it by yellow. So as you can see, as long as the algorithm does not run out of available colors at each step, then the algorithm will continue, and we can color the edges of HM properly if the algorithm runs for M step. Our main claim is that we can show that that is actually true. So with high probability, we can color M edges properly with those Q colors. So we claim that is our main claim. So to prove this main claim, we only need to show that at each step, the number of available colors is greater than 0. And we prove that by some differential equation method, which will use our pseudo-random assumption of the host graph H, where the host graph H is nearly regular and has small codegree. Therefore, by differential equation method, we can show that with high probability for all the edges of the host graph H and all the steps before I, the number of available colors for each edge E after I steps, which we denote by QEI, is roughly this parameter to the power of K times the number of original possible colors, Q. By differential equation method, if we can show this kind of result, then actually that implies that we can color all the images properly with Q colors with that probability. That is because this parameter is much greater than 1. Because if you observe this parameter, it takes the minimum when I is as large as possible, which is M, and K is as large as possible, where we require the uniformity of K is roughly some constant B times log N. So that is this part. And because we assume that M is not too small, therefore you can figure out that the parameter Q is at least N to the sigma. And then if you do some mathematical computation, you will figure out that this term is at least N to the minus B over delta plus sigma. And because there is some relation between delta and B and sigma, you can figure out that this term is positive. So the minimum number of available colors of all edges over all the steps before I is much greater than 1. So we do not run out of available colors. Therefore, the algorithm continues and colors the edges of HM properly with Q colors. Therefore, we prove our main claim and we prove our chromatic index result for random sub-hypergraph. Okay, then before the end of this talk, I would like to mention one of the open problem. So as a recap, we show that with high probability, we prove that the order of magnitude of the click chromatic index of a binomial random graph GNP is N over log N. So an open problem is to determine the asymptotics of this parameter, not just the order of magnitude. And let me give you some clue about the asymptotics. So someone may guess that the simple lower bound is correct. So what is the simple lower bound of the click chromatic number? So we have seen it before. So because we need to cover all the edges into this vertex by clicks, so we need at least the maximum degree of GNP over roughly the size of maximum clicks. We need at least so many clicks. And for all the clicks to continue this vertex, they need to receive different colors so that the clicks in the same color class are vertex disjoint. Therefore, we need at least so many numbers, so many colors. And as we have seen, this number is roughly this one. Therefore, someone may guess that the asymptotics is the simple lower bound. But actually, that is not true because this simple lower bound can be improved. The constant factor in this simple lower bound can be improved to 1 plus some function f. And this function f, for all the p, this function is positive. And especially when p equal to 1/2, this function is equal to 1. So p is 1/2 is one of the most interesting case that the binomial random graph Gn 1/2 just take all the n-vertex graph uniformly at random. So it says that the lower bound can be improved by a factor of 2 in that case. Therefore, the simple lower bound is not correct. Therefore, it's unclear what the asymptotics of this parameter should be. Okay, so let me wrap up this talk. So in this talk, I introduce the Prague dimension of graph G. So that is the minimum chromatic index over all click covering of the complement graph G. And we prove that with high probability, the Prague dimension of binomial random graph GMP has order of magnitude n over log n for all constant p. So our result verifies a conjecture of Füredi and Kantor. And to prove our result, we find a click covering by semi-random algorithm, which is also called Rodoniibo Method. So that click covering C is just the union of some subcollections. And we bound the chromatic index of each subcollection by our chromatic index result for random hypergraph. And to prove the chromatic index result for random hypergraph, we use the random greedy Kalen algorithm and differential equation method to analyze. And here, one of the key new tool of our analysis is the chromatic index result for random hypergraph. And this chromatic index result allows the hypergraph to have edge of size log n, not just constant. So that is our main tool. So as the open problems, one is what I mentioned. So we determine the order of magnitude of Prague dimension. And the open problem is to determine the asymptotics, not just the order of magnitude. And when p is a function depending on n, when n to 0 as n tend to infinity, we also determine the asymptotics of the click chromatic index of random graph GMP, so which is the Prague dimension Gn1 minus p. So we determine the asymptotics in this case, but there are some gaps. So it will be interesting to close the gaps in the range of p. Okay, so let me stop here. Thank you.
Thank you very much. Let us all unmute ourselves and thank Kay. Are there any questions?
Perhaps one question. I should probably ask Vojta this, not you, but it seems like such a natural question to ask, what is the Prague dimension of an Erdős-Rényi graph? Why did it take 40 years for somebody to ask this question?
Yeah, actually, we find this this question in this work, in Füredi and Kantor work. They ask a question about the Prague dimension of this one, because they determine the maximum degree, which is bigger than this kind of result. So they ask this question.
I should say though, there's one paper from 1981 or 1980 where Nešetřil and Rödl both already consider p equals to 1/2 to, I think, prove a non-trivial lower bound or something. Like they give basically this lower bound construction that we have, or the simple lower bound construction that the Prague dimension is large. They have that in a paper from 1981. So kind of the study of random graphs can be traced back to then, to already very close to after it was introduced.
I see. So they just didn't get around to actually conjecturing that their lower bound was the correct answer.
I think so. I think once you see the lower bound, you're kind of tempted to maybe even believe it's the correct constant, but definitely the order of magnitude, I think one is convinced that that should be the right.
Yeah, and obviously they were right. Yeah, they would have been right, yes.
But the constant, I think, is tricky. At least we were surprised that the constant is different than the trivial one.
Yeah, it would be interesting to get that.
I think for that, someone would need to understand better how to enumerate these click covers. Like if someone can enumerate them in some clever way, that seems to be missing.
Mm-hmm. Well, thank you again for a very nice talk, huh?
Yes. Thanks for attending.
Nice result. Both of you, all three of you.
Okay, are there any more questions? Actually, I have a quick question. You say at the end of your talk, you said that you can also consider this, I guess, click cover parameter when p goes to 0. But I guess from the point of view of the Prague dimension, it's also interesting to look at the case where p goes to 1 with n. So the click cover index of G and P for p going to 1 with n. Do we know something about that regime?
Actually, we have some lower bound. So lower bound will be fp, but the case is that when p tend to 1, this function will tend to infinity. Therefore, it's unclear what happened of the order of magnitude when,
I see. All right, any more questions? Comments? If not, then let us thank the speaker again.
Yeah, and thanks for attending.
Thank you for a very nice talk.